Okay, so welcome to the session of solving problems that don't exist yet. Second edition. So for the first talk, we'll have Clémence telling us about reducing the number of qubits in quantum factoring. The floor is yours.
Thank you very much for the introduction. So today I will present to you a memory optimization of Shor's algorithm, which is a quantum algorithm that allows, among other things, to factor integers. Please note that this is a joint work with Pierre-Alain Fouque and André Schopenhauer. Before diving into the details of how our reduction works, I'm going to talk a little bit about the original Shor's algorithm. Let's assume from now on that we want to factor an integer big N that is a product of two distinct primes, since this is the application case that comes from the RSA crypto system. The idea of Shor's algorithm to do so is you will take at random an integer a modulo big N. You will find the multiplicative order x of a in z over nz. And then if x has the right properties, you're able to deduce the two prime factors of big N from that. The part where we need a quantum computer here is the second step. So in order to find the multiplicative order of A, what we are going to do is we are going to take a register S and we are going to put into this register an equidistributed superposition of every pure state representing the pairs x, a to the x modulo big N, where x goes from 1 to an order of magnitude of big N, basically. Once we've done that, we apply a quantum Fourier transform on the input part of this register, so the part of this register that contains the x values. And we do a measure on the input part of the register, and we are able to deduce the order of A in Z over NZ from that. If this is your first time seeing a description of Shor's algorithm, maybe things are a little bit unclear at this point. Why does this work? Basically, the idea is that, roughly speaking, one of the things the Fourier transform allows to do is that it allows to exhibit the periodicity in a sequence of numbers, all right? The thing is, in the output part of our register, we have a sequence of numbers of the form a to the x with x that goes from 1 to an order of magnitude of big N. And since this sequence of numbers specifically is periodic, and its period is the multiplicative order of A that we are looking for by design. So actually, what happens when we apply the quantum Fourier transform in the input part of the register is that we are able to exhibit the period of the sequence of number that is stored in the output part of the register. And this is why this algorithm works. Now, since we have to store integers that are between 1 and big N in order to instantiate and to run Shor's algorithm, this algorithm has a memory complexity that is linear in the bit size of the integer big N that we want to factor. So let's name this bit size small n. The space complexity of the original Shor's algorithm is linear in small n. All right? Now, there's a typo in the slide. This says the best memory complexity currently is This should be actually, before our work, the best memory complexity of Shor's algorithm was 1.5 times n plus a very small amount of qubits, and it was due to memory optimization presented by Zalka. Of course, you probably know that building big quantum computers is something extremely difficult, and we are progressing slowly on that matter. If we want to be able to factor, for example, integer big N that have a bit size of 2048 qubits, we will need currently a quantum computer that has millions of physical qubits. We don't have that yet, so hence the importance of trying to reduce the memory complexity of Shor's algorithm. In that regard, what we achieved in this work that I'm going to present to you is that we bring the memory complexity of Shor's algorithm down to n over 2 plus a negligible amount of qubits. I will talk about it a little bit later, but some other researchers have improved upon our work and have been able to propose an even better complexity. We will see that at the end of the presentation. The first thing we do in order to obtain this memory optimization is that first we are going to reuse previous memory optimization that is due to Ekera and Hastad, and that allows to reduce the size of the input register, or the input part of the register that we use specifically, down to n/2 plus a negligible amount of qubits. This optimization is very practical, but it doesn't affect the size of the output part of the register. So now the natural question that we can ask is it possible to do something about the size of this output register? So in order to do that, we are going again to use an ID that is due to May and Schlipper this time, and that was sketched in one of their papers, but only theoretically. The idea of May and Schlipper relies on the following observation. If you have a sequence of numbers that is periodic and a hash function, if you hash every number of your sequence in order to obtain a new different sequence of number, the second sequence will also be periodic, and if your hash function has the right properties, the period of this new sequence of number will be the same as the period of the first sequence of number. This observation gives us the following idea. We could use a register S that contains superposition of states that represent pairs of the form X and a hash of a to the X modulo big N in order to run Shor's algorithm. And if we have a hash function that allows us to compress the size, how do I put this? If we have a hash function that gives us an output that can be stored on fewer qubits than what we need for a to the X modulo big N, this would allow us to use an output register that would be way smaller than what we need currently in order to run Shor's algorithm. This is exactly what we are going to use, and the hash function that we are going to use specifically is this kind of hash function that sends an integer z to z modulo 2 to the r. So basically, h sends z to the first r bits of its representation. This means that in order to represent the hash of a to the x modulo big N right now, we only need an output register that contains r qubits. And we can choose r to be relatively small. So this is a nice idea. The problem is that we can't compute a to the x modulo big N and then modulo 2 to the r naively. All right. This difficulty is why May and Schlipper, only sketch their ID theoretically. The problem here is that if you compute a to the x modulo big N and then modulo 2 to the r naively on your quantum computer, at some point you will have to compute a to the x modulo big N, and you will have to store that on your quantum computer, which will still take an amount of qubits that will be linear in small n, which is exactly what we want to avoid. So now the difficulty is how do we obtain the result we are interested in without using that much qubits? We will start from the naive computational sequence that I just mentioned, and we will see how we can modify it to obtain what we want. The first trick that we are going to use here is actually a very standard trick when implementing Shor's algorithm for factorization. The idea is that we are going to write x in a binary mode right like so, which allows us to rewrite a to the x as the following product right here. Now assume that we set a to the I parenthesis to be the smallest positive integer that is equal to a to the 2 to the I modulo big N. In this case, we can also write a to the x modulo big N as this kind of product right here, modulo big N. This is a consequence of the fact that, you know, a times b modulo big N is equal to a modulo big N times b modulo big N. This way of computing a to the x modulo big N is useful for us for two reasons. The first one is that the a to the I parentheses we can pre-compute, and so we don't have to deal with them on our quantum computer. The second reason why this kind of technique is useful is because, by definition, the A to the I parenthesis necessitates n bits to be represented, and so this means that this quantity right here that we have to compute prior to the modulo big N operation is at most n squared bit long. All right. So now our computational sequence has changed, and we want to compute this quantity y that we just defined, and then modulo big N, and then modulo 2 to the r. From that point, the general idea for optimization will be the following. We will compute y by computing this quantity modulo a set of several small prime numbers p, and we will retrieve the quantity y by computing y modulo the product of every prime p using the Chinese remainder theorem. This whole computational technique is called the residue number system, actually. Then, in order to compute the modulo big N operation, we will use Barrett's reduction trick instead of the Euclidean algorithm. And at the end, we just apply the modulo 2 to the r operation, which is actually a bit truncation, so it's a free operation. So let's detail a little bit how we compute y precisely. We saw just earlier that y is at most n squared bit long. So it's automatically smaller than 2 to the n squared. Let's assume now that we have an integer big M that is a product of several distinct small prime numbers, P1, etc. to PL, and that M is such that M is bigger than 2 to the n squared. We know that the ring of Z over MZ is isomorphic to this kind of field product right here. And the Chinese remainder theorem tells us that y modulo big M can be written as this kind of sum right here involving the product of y modulo each pi and some cofactor. So again, we know that y is always smaller than big M, so we know that y modulo big M is equal to y, and this gives us a way to compute the quantity that we are looking for. Again, this formula is practical for us because first, every cofactor involved in this formula we can also pre-compute, and second, the y modulo p are actually very small quantities. You see that we can choose each pi in this product right here to have a bit length that is like at most log small n, which means that likewise the y modulo pi will have a bit length that are at most log small n. So we don't need a lot of space to compute and store them. So now again, our computational sequence has changed, and now we want to compute this quantity right here that is due to the Chinese remainder theorem, and then modulo big M in order to obtain y, and then modulo big N, and then modulo 2 to the r. We are starting to have a lot of modulo computations here, and this is actually a quite costly, in our context, computation to carry on a quantum computer. So in order to ease things down for us, we will use Barrett's reduction trick in order to compute these modulos. So precisely what Barrett tells us is that the integer parts, you can find an integer u such that the integer part of z divided by big M will be equal to this kind of integer part right here with very good probability, depending on u. This is useful because, again, the integer part of 2 to the u divided by M we can pre-compute, and the integer part of an integer divided by a power of 2 is a bit truncation. Okay, you just get rid of the first u bits of the representation of the integer in the order. This means that in order to compute z modulo big M, we can compute z modulo z minus the quotient of z divided by M times M, and this is equal to this kind of formula right here with good probability. Of course, this kind of trick can be applied with big N instead of big M too, and this is how we compute the two modular operations that we have right here. This means that, again, our computational sequence has changed, and now we have to compute these two quotients right here, and we can observe actually that a to the x modulo big N is equal to this kind of sum right here. Now I'm going to ask you to make a leap of faith and trust me on what is going to follow. We can actually express these three quantities, Z, Q big M, and Q big N, as this kind of sum, okay? What I want you to notice at this point is that all of these sum are expressed relatively to the prime factor P of big M, okay? This means that in order to compute these three quantities, what you can do is that you can take a small register that will be used to compute Y modulo, for example, P1, and then you update every of this quantity according to the formula that you are following. And then you can reuse the small register that you just used to store Y modulo P1 in order to compute Y modulo P2 to store it and to then update these three quantities and so on and so on, which means that you can use one register of log small n qubits in order to compute every value of the form Y modulo P, all right, which actually saves a lot of space since maybe, I mean, if you remember, we saw that we can choose the prime numbers P very small, like of bit size log small n, but they are actually roughly n squared divided by log n of them. And so if we had to use different register every time we have to compute Y modulo, some Y modulo P, this whole optimization wouldn't work. So this is actually an important reason why the whole optimization ends up working out. Okay, so as I told you earlier, this allows us to achieve space complexity of n over 2 plus a negligible amount of qubits instead of previously 1.5 times. There should be an n here plus a very small amount of qubits. This means that concretely, in order to factor a 2048-bit integer, we need 1,730 qubits, which is less than what we need to store the actual integer. So not bad, in my opinion. Of course, this optimization isn't free. It comes with a gate count overhead, but you can notice that the depth of the algorithm doesn't change from the depth of the original short algorithm. Now, to conclude this talk, I want you to, I mean, if there is something to remember about this talk, is that the key tools that allow this optimization to work are the residual number system, the Barrett selection trick, and the successive computation of the Y modulo P on the same register every time. There are some open questions that are left at the end of this work. The first obvious one is, can we use this kind of computational trick in order to optimize the memory cost of shores when solving the discrete logarithm problem on elliptic curves? The other question that we had at some point is, can we reduce the gate count overhead? And actually that answer has been solved by the time, and there is a paper by Craig Gidney that shows that you can actually make the gate count overhead completely negligible for this kind of optimization. And this paper actually improved on the memory optimization that we obtained previously, and they show that they are able to factor a 2048-bit integer with only 1,000 and roughly 300 qubits. So actually, things have improved since the publication of this paper. Thank you very much for your attention, and if you have questions, now is the time.
We have time for one quick question. You can go to the microphone in the front. There's one.
Thank you for the talk. So I have just one question. When you say that you want to optimize short for factoring any kind of integers, are you thinking something? Are you thinking something? Sorry, is it not on?
It's just too low for you.
Okay. So speak close to it. Okay. So when you say that you want to optimize Shor's algorithm for factoring any kind of integers, are you thinking of sort of applying this to Cypher's variation of the algorithm, or are you thinking of something more, something beyond that?
You mean regarding
the sort of open questions on factoring any kind of integers. So Cypher also has this kind of trade-off idea where you could go down to like n plus something or something like this, which might be below Salka. Is this what you had in mind as an open question, or is it something else?
I think I thought briefly about that, and if I remember correctly, and if I understood your question well, it's the Ekera-Hastad optimization that causes problem when you want to deal with like any kind of integer.
Yeah. So that algorithm is for RSA integers or integers of special form, but there is also an earlier version by Cypher that sort of cuts the register from like 2n to n plus epsilon bits by doing multiple runs and then doing things. I can show you later.
Yeah, that would be very nice.
Okay, quick question.
I have a quick technical question. You say that you use the hash to encode a power x. Yeah. What if there are hash collisions?
Sorry, what if?
What if there are hash collisions? And if there has some hash collisions, and you use QFT and to measure. Oh, is that matter?
Okay, something that I didn't mention in this presentation is that actually the hash function works on the principle that you apply a modulo 2 to the operation to the integer, but there is also a randomization process into it. So every time you run this algorithm, actually you are going to you are going to use a slightly different hash functions that still outputs something that can be stored on R qubits, but there's a bit of randomness in it, and I think that solves the kind of issue you're raising, basically.
It means that you have used some more complicated hash functions.
Yeah, actually, like, I didn't mention it because the proof of why this works takes like 4 pages in the paper.
Yeah, understand, yeah.
But yeah, I mean, if you're interested in that, you should look into it, I think.
Okay, thank you.
Okay, let's thank the speaker again. So the next talk is going to be given by Hansrad and Trung. So we'll start as soon as they set up.
This one's only gets the handheld. So. Okay. Take that off. Just come down.
I don't miss this one anymore, guys. Yes.
Forward, backward.
Okay. Nice. Okay.
Okay, so let's welcome Hansrad and Trung on their talk on a quasi-polynomial time quantum algorithm for EDCP over power of 2 moduli.
Thank you for the introduction. So today, me and my colleague Hansa, we will talk about our quasi-polynomial time quantum algorithm for the extrapolated dihedral coset problem over power of 2 modules. So this is the joint work of Shibai, Elena Kisanova, and William Humans. So first, let me talk about our motivations. Oh, okay, sorry, my bad. So let me talk about our motivation when we start these projects. As you know, like a lot of cryptography scheme, especially for lattice-based scheme, the hardness of the cryptography scheme relies on the hardness of the learning with error problem. This is actually come from the remarkable paper of Regev in 2005. So our goal is we want to understand quantum and logically complexity of solving this problem. So there are so many approaches to try to understand the hardness of learning with error. The first approach is we try to reduce learning with error to some lattice problems such as the approximate sorted vector problem, and then we use lattice reduction to access the underlying assumption. Another approach is we try to reduce it to some well-studied quantum problems such as the Dihiro-Coset problem or the hidden subgroup problem. So we interest into the second approach because in 2018 there's a paper of Braketsky, Kisanova, Stelle, and Wentz. They show that there is an equivalent between learning with error and the extrapolated Dihiro-Coset problem, where the extrapolated Dihiro-Coset problem is just a generalized version of the EDCB under some certain parameter. So first, so our question is, what is the complexity of EDCB? If we can understand the complexity of EDCB, maybe we will have a better understanding about the complexity of the learning with error. So this is our motivation when we first start this project. So in this talk, we will present our quasi-polynomial time and sample quantum algorithm for the extrapolated Dihiro-Coset problem. So first, let me introduce quickly about the learning with error. So the first version of the learning with error is to recover a series S in G and Q given a linear system that you have seen here, where AI is uniformly sampled from GQN and the scalar error EI is from some distribution. Typically, the error distribution is the discrete Gaussian distribution. So another way to consider the learning with error is the matrix form. So where we can consider, we have to recover a series S given equation B equal to A times S plus E. So the harshness of the learning with error actually depends to the parameter alpha, where alpha is just a quotient between the noise and the modulus. So in general, the smaller the alpha, the easier the learning with error problem. In LWE standard setting, the size of modulus Q grows polynomially in terms of n and m equal to n log Q. The distribution for the error is the discrete Gaussian distribution with the standard deviation is around square root of n. So the best algorithm to solve LWE, as we know, is run in exponential time. So now I want to talk about DCB and EDCB. So they both ask the same question. So given some quantum state, can we recover a series F? So the difference between DCB and EDCB is generalized DCB using multiple shift, and the amplitude is sampled from some distributions, from some bounded distribution D. Here xi and x is a vector of dimension n. So depend on the distribution of the amplitude, we have a different variant of EDCB. For example, if the distribution is Gaussian, then we have the definition of Gaussian EDCB, and when the distribution is bounded uniformly distribution, then we have the definition of UEDCB. And as I talked in the beginning, when n equal to 1 and m equal to 2, EDCB become DCB. And in the same paper of BKSW in 2018, they showed that Gaussian EDCB actually equivalent with the uniform EDCB. Next, I want to give a quick summary about the relation between LWE, DCB, and EDCB. So the first result is the reduction from LWE to DCB. So this result, it came from Regev. So this is a probabilistic algorithm. So what he gets, he gets a perfect quantum sample of DCB with some probability. So even later, Kuperberg present a sub-exponential time to solve DCB. It won't lead to any sub-exponential algorithm for LWE. And in the, as I mentioned in the beginning, by the same author, Braketsky, Kisanova, Stella, and Wen in their paper in 2018, they saw the equivalent between LWE and EDCB. So under some constraints, and these constraints, we will discuss more about this constraint when we talk about the impact of our algorithm on LWE. And of course, EDCB can easily reduce to DCB. We just increase the modulus from Q to the N. And in this work, we try to fill the gap of the result by solving a Warshik polynomial time to solve EDCB. So first, let me give you an overview picture about the complexity of the uniform EDCB. So we try to modelize the complexity of EDCB using two factors, the number of samples and the number of shifts. The more shifts we have, the easier the uniform EDCB. Like for example, when m equal to q, we can solve the EDCB using quantum Fourier transform in polynomial time. And when m equal to q minus c or q divided by c, where c is a small constant, we can solve it using Arrow-Rage or in some of related work in the paper of CLZ 2022. They present a quantum filtering algorithm, which is a quantum version of Arrow-Rage to solve UEDCB in polynomial time. So the uniform EDCB is hardest when m equal to 2, m has the sign of poly n. So when the number of samples is sub-exponential to the square root of n, we have sub-exponential algorithm to solve UEDCB. And when we have less sample, the best algorithm we know is exponential. So the blue area that you guys see here, this is where our algorithm applies. And the red area that we mark here, this is where our algorithm improves the state of the art. So here I want to emphasize that our algorithm only applies when the modulus Q has a form of power of 2. And the best complexity we have is quasi-polynomial, which is n to the power of log Q. So next I will leave the stage for Hansa so he can discuss about how we actually implement the algorithms.
Thank you, Tran. So before looking at our main algorithm, I will quickly look at the Kuperberg's algorithm, just give an overview of the Kuperberg's algorithm, how it works, because we kind of like replicate the Kuperberg algorithm in the case like for ADCP. So in the Kuperberg algorithm works for like dihedral coset problem. And suppose we are given this quantum state of this form, and first like we do the quantum Fourier transformation for the second register, and we measure it. So we get a quantum state of this form where y is also known classically, and we have a quantum state of this form. So what Kuperberg's algorithm do is like, suppose we are given these kind of quantum states, can we combine these quantum states and can we generate a quantum state of like this form, like psi n over 2 is equal to 0 plus this kind of quantum state. So in Kuperberg's algorithm, like they combine two samples and they reduce the modulus n to 2, and we get like this kind of quantum state. And once we have this kind of quantum state, we can measure in Hadamard basis, and we can recover the one last bit of secret S. So that's what we're gonna do in our algorithm, but the middle steps are different. So the Kuperberg algorithm it's sub-exponential, and it needs like sub-exponential number of samples because like in his algorithm we start with sub-exponential number of samples and we combine them and we make last square root of log n entries 0. And since the depth is also square root of n, so the total number of initial samples we need is sub-exponential. Okay, yes. So yeah, like let's look at the Kuperberg algorithm and our algorithm also simultaneously. So we have UEDCP in the Kuperberg's case, n is equal to 1, and in our case, we have a vector form. So suppose we are given these quantum states, initial quantum states. The first thing we do is like we apply the quantum Fourier transformation on the second register and we measure it, and we get the samples like this y and a quantum state. And in our case, our y is a vector form, and I will call this sample as a UEDCP bar sample. So in the merging step in Kuperberg's algorithm, we merge like two quantum states, and we get like after tensoring those quantum states, we get this state. But in our case, we combine n+1 many samples, and we get a quantum state of this form. So the capital Y is a matrix which is n times n+1 because we are combining n+1 number of samples. And in the Kuperberg's algorithm, we recover one bit, but in our algorithm, we recover least significant n bits. So that's where we are taking the advantage. That's where we improve the time complexity. Okay, so first, like I will look at the main step of the algorithm where we have n+1 many samples of UEDCP bar, and we combine them and we get a 1 UEDCP bar sample with new modulus, which is Q/2. So that's the main step of the algorithm. And how we do it, first, suppose we are given n+1 many UEDCP bar samples, we tensor all of them, and we get a quantum state of this form where this capital Y is known classically, and it's uniform because capital Y, the columns of capital Y are the Yi's which we get through all these samples. So the next thing we do is we compute this Y times J mod 2 in new register, and we measure it. So like once we compute Y times J mod 2 and we measure it, our J will be restricted to J will be restricted to only the solution of this system of linear equation. And remember, like this capital Y is uniform modulo 2. So it has full rank with constant probability because the columns of Y are uniform modulo 2. So it has full rank with constant probability. So we can say that because it's a n by n+1 matrix, so the solution set of this system of linear equation is J0 and J1. So this state in step 2 is exactly of this form. Exactly of this form where we have like J0 and J1, which are the solution of this system of linear equation. And once we have this form, we can take out the global phase and just rewriting the basis, we get a quantum state, which is like very similar to the state like we started with, the EDCP state with which we started with. And there is another thing is like since J0 and J1 are the solutions of this system of this linear system, so Y J1 minus J0 is E1. And that's why we can rewrite this quantum state as this form because Q is power of 2. This algorithm works for Q is power of 2. So we can rewrite as like this quantum state where the new Q is Q/2 and Y prime is also known because the capital Y was known in the starting and we know the solution of this system of linear equation, which is J0 and J1. So that's how, this is the one step of the algorithm where we go from UEDCP bar mod Q to UEDCP bar mod Q/2. Now, since we want to combine in such a way that we get a UEDCP bar mod, a UEDCP bar with modulus only 2. So Q is power of 2. So we need this kind of chain of combinations. So if we start with, so like at each step like this, we combine n+1 many number of samples, and we need log Q many steps. So total number of samples in the starting we need is n to the power log q, because at each step we absorb n+1 many samples, and we are going from q to q is power of 2, so q to only 2. So we need like n to the power log q number of samples, which is 2 to the power big of log square n. And that's the final stage, final sample we get after this chain of combination. And if you see now, if we measure this quantum state, and we have these n many quantum states, if we measure them, we get like yk comma yk inner product with s modulo 2, and these are n many, so we can use Gaussian elimination to recover S modulo 2, which is the last bit of secret S. So yeah, like once we measure in Hadamard basis, we can get YK inner product with S modulo 2. And we have n many of these samples, these equations, we can recover the last bit of secret S. And we can continue, like we can, this one chain of reduction, chain of combination will give the last bit of secret S. Similarly, we can get the other bits of secret S also. Okay, after that, I want to quickly look at the application of this algorithm on other problems, which are other lattice-based hard problems. So the first one is, okay, sorry. Yeah, so this here, like we defined only for m is equal to 2, but this, we can say that this algorithm works for general m, because we have this reduction by this Dolansky's paper, where UEDCP reduces to like UEDCP bar, UEDCP with different m. So if you can solve a UEDCP for smaller m, we can solve a UEDCP for any m bigger than that m. So using this reduction and our algorithm, we can say that we have a quasi-polynomial time algorithm for UEDCP with given quasi-polynomial number of samples. And yeah, now I am going to look at the application of this algorithm for other problems. So there is a quantum version of LWE, which was introduced by CLG, paper 2022. In this problem, it's like we are given this quantum state of this form, and where AIs are known uniformly, and the problem is to find S. So our algorithm applies for this problem also, since we have this chain of reduction, like SLWE reduces to GEDCP bar, and GEDCP bar reduces to UEDCP bar with small change of parameters. So the previously best known algorithm for SLWE with Gaussian amplitudes was sub-exponential, but in this paper, we have an algorithm for SLWE, which takes times as quasi-polynomial and needs only quasi-polynomial number of samples. And the last thing I want to mention is like, what's the impact of LWE? Because that was the motivation, because we have a connection between LWE and EDCP. So that's why we are interested to look at the hardness of EDCP. So in the BKSW paper 2018, we have they introduced the reduction from LWE to EDCP, but it has a restriction on number of samples. This reduction only produces polynomial number of samples. This reduction, but in our algorithm, we need polynomial number of samples. So for the standard parameter, for the standard parameter of LWE, we don't have any impact on LWE. So since our algorithm needs like quasi-polynomial number of samples, and this reduction only yields like polynomial number of EDCP samples. So our algorithm does not impact the standard LWE. And these are the future questions we have. So like there are two things we can do is like, first thing is like, can we improve the reduction from LWE to EDCP? Can we improve that, like, which can give like more samples than polynomial? And the other thing is like, can we modify our algorithm which needs only polynomial number of samples, but even if it takes sub-exponential, in that case, we would have a algorithm for LWE, which works in sub-exponential time. And yeah, like this algorithm only works for when Q is power of 2. Can we extend this to like non-power 2 modulus? And okay, the last since we have a like reduction between LWE and EDCP, can we have some connection between structured LWE and like some variant of EDCP, and that which is more efficient? And thank you. That's all.
Because we are running low on time, maybe we'll take the questions offline.
Okay.
Yeah, maybe we'll have the third speaker set up. I guess while she's setting up, is there a quick question?
Presentation. Should you get forward, backward? That's right.
Thanks.
Okay, yeah, I'll be talking about quantum state group actions, and this is joint work with Mark Zandri. So I'll start by talking about groups and how they're used in cryptography. So in this work, we'll consider a billion groups. So a group is a pair G star consisting of a set G and a binary operation star, which takes two group elements and outputs another group element. And we say it's an abelian group if there's an identity element. So E star A equals A for all A and G. For every element in the group, we have an inverse element such that when you combine them with the star operation, you get back the identity element. And associativity basically says that the order in which you combine, in which you apply the star operation doesn't matter. That's the main idea. And then the last is just because the group is abelian. Okay, and groups have been used in there's many hardness assumptions on groups, on cyclic groups, and these assumptions are useful to build crypto systems that are secure against classical adversaries. So one concrete example of this would be discrete log, the discrete log assumption, where we're given a group element G, and we're given G to the A, where A and the task is to find A. And no computationally bounded adversary should be able to find A. And this hard problem is the base of many classical crypto systems. So now, if we want to switch to post-quantum cryptography, which is cryptography that is secure against quantum adversaries, we cannot use this discrete log assumption on groups. And that's because quantum computers break cryptographic groups, and this is because finding discrete log is easy. So, and you can do this with Shor's algorithm. So suppose H equals GA and we want to find A. This is exactly the problem we want to solve in discrete log. So we can define a function f, which takes as input x and y and outputs g to the x, h to the y. And it's easy to see with some easy algebra that f is periodic. So f xy plus negative a1 will give you back f of xy. So if there's an algorithm that can find this period, which is negative a1, then A can be recovered and we can break discrete log. And we know from Shor's algorithm that quantum algorithms can easily find periods. So this assumption will be broken with quantum computers. So how can we hope to use problems of similar nature in a quantum secure manner? And we do this by making use of something called cryptographic group actions, which were introduced in 1991. And we say that an abelian, you can think of this as like a less structured version of groups. And an abelian group G acts on a set X. Now there's a set X in a group action, and the action is some star. And there's an identity element in the group G, and E star X for all set elements X would equal X. And this compatibility property is just saying, again, the order in which you apply this action doesn't matter. So you could apply H, you could act with the group element H on the set element X, and then act with G on the resulting set element. Or you could combine G and H using the group operation and then act on the set element. So it should be the same. And the analogous discrete log assumption on group actions would just be X, given X and G star X, find G, and this should be hard to do, or that's the assumption. And groups are a special case of group actions. So you can think of Z sub P as the group and the set as the group G, and Z sub P would act on G via A star X equals X to the A. So in this setting, the discrete log assumption on groups, and when you write the group action as a group, then it would be the same assumption on groups. Okay, so now I'm going to talk about groups again for a minute. So how do we justify the security of a group? We have a classical group and we have a classical attack, classical adversary against our group. There are two main steps. The first step is to prove the security under the hardness of some computational problem on the group. And then the second step is to justify the hardness of this problem that we assumed to prove security. And when we're dealing with groups, then we can justify this hardness if we're considering adversaries that only make black box access of the group. So if there's an adversary that's querying the group in a black box manner, then we can justify hardness of, say, discrete log on groups. But moving to group actions, the first step is still the same. We can, now we have a classical group action and we have a quantum adversary. And to justify security, the first step is fine. We prove security under hardness of some computational problem on the group action. But it's not clear how we justify hardness of the problem. And this is not clear because even in the generic model, so even in the model where we have an adversary that's making black box queries to the group action, we have algorithms with polynomial query complexity, but they're inefficient, that break these crypto assumptions on group actions. So it's not, so unconditional lower bounds are not possible even in the generic model where the adversary is just making black box queries to the group action. So this is the motivation for us to consider in this work quantum state group actions and try to prove unconditional hardness for similar assumptions on this quantum state group action that we introduce. Okay, so that I'll formally say what a quantum state group action is. And a quantum state group action, it will consist of, it will be based on some underlying classical group action with the same definition that I mentioned before. And classical group action, G, X, star. X is the set, G is the group, star is the operation. And now instead of, now we have a collection of states as our set instead of just the set X. So we have a collection of states that is indexed by all elements in the set X. So that's kind of, I guess, the main difference. And then we have a distinguished starting element. This could be any element in the underlying classical group action. And the corresponding starting element of the quantum group action would be psi x star. So this is the quantum state indexed by the starting element of the classical group action. We have a efficient quantum procedure start, which produces the starting element. And then we have a procedure act, which given a group element G and some set element states psi sub x, the act procedure acts on the set with the group element G. So it produces G star psi sub x, which for correctness we'll think of as psi G star x. Okay, and we assume for this work or for this talk that G star x and x is a bijection. So the map, so the underlying group action is regular, and this map is a bijection. And we say that our quantum state group actions are orthogonal if for all x, y, and big X, the corresponding states are orthogonal. So psi x is orthogonal to psi y for all x, y, and x. Okay. And one thing to note is that now, because our instances are quantum states instead of classical strings, these quantum states are, it's not necessarily easy to copy them, or in other words, they're not necessarily clonable. So the hard problems on our quantum group action will be parameterized by the number of copies of the instance that we give. So as an example, the LDDH assumption on quantum group actions would be given L copies of psi A, L copies of psi B, and L copies of psi A plus B. This should be indistinguishable from L copies of psi A, L copies of psi B, and L copies of psi C, where C is random, some random element. And similarly, the L discrete log assumption would be an adversary that's given L copies of psi G star, the starting element. It should be hard to produce G. So this is the L discrete log assumption. And we say that an assumption in general is hard if it's hard for all, if it's L hard for all polynomials L. Okay. Oh. Okay, so one last assumption that I'll talk about is the generalized matrix problem. And this problem essentially encompasses the LDDH and the L discrete log assumption. And special cases of this generalized matrix problem also give us newer assumptions that are used in classical group actions, but whose hardness has not been justified. Okay, so now formally, the generalized matrix problem is just a family of matrix assumptions that's parameterized by some matrix over integers, and we consider the following two distributions. So first, consider a tuple of a set of these quantum states, psi g1 through psi gn, where this vector g is produced by multiplying the matrix M with some secret vector S. And that's the first distribution. And the second distribution is just psi g1 through gn, where g1, this vector g, is just uniformly random. And the assumption is that d0 is indistinguishable from d1, even if we're given M, but we shouldn't be given S or G. So the secret shouldn't be given and G shouldn't be given, the vector. Okay, and for more intuition, DDH is just a special case of the generalized matrix problem if you instantiate this problem with this specific matrix M. So if you take this matrix and you take two random elements, then you would get A, B, and A plus B, which is the first three cases in DDH. Yeah. Okay. Yeah, and also, like I talked about, if we generalize this assumption to non-uniform secrets, so some secrets that are binary but with some high min entropy, then we get something called the linear hidden shift assumption. This has been used to build proofs of quantumness. I won't go more into detail. And if we also generalize GMP to a structured matrix, then we get something called the extended linear hidden shift assumption. These are all assumptions on classical group actions whose analogs we can get in the quantum group action setting. Okay, so the main results that we have are as follows. So we introduce a hash-based, or we come with a hash-based construction of quantum state group actions, and we prove that the generalized matrix assumption, which encompasses the DDH assumption and the linear hidden shift assumption, it's unconditionally hard when our constructions instantiated with KY's independent hash function. We proved that it's computationally hard when this hash function H is lossy. And we proved that it's unconditionally hard with query-bounded security in the quantum random oracle model. And the last two results, they give us orthogonal quantum state group actions, and the first one is non-orthogonal. And the second main result is that when this hash-based construction is orthogonal, so when it's of the last two cases, then there is a query-bounded, computationally inefficient quantum co-sampling attack that works to break the assumptions on our quantum state group actions if enough copies of the instance are given. So like I talked about before, there already exist quantum algorithms against classical group actions. these algorithms generalize to quantum state group actions if this construction is orthogonal, and second, if we're given enough copies. So all of our security is based in the bounded copy setting for orthogonal group actions. So yeah. Okay, and the third main result is that we unify two existing quantum money schemes. So in Zenry in 2024 constructed quantum money from classical abelian group actions. And it's easy to generalize this construction to a quantum state group action and then instantiate with our hash-based construction. Doing this, we recover a previously known quantum money construction from non-collapsing hash functions, also by Zenry. So the quantum state group actions sort of unify these two already existing quantum money constructions. Okay, so now I'll go a little bit into detail on what the hash-based group action construction is. So we need, of course, a hash function, and we need some starting state, which should be efficiently constructible. And the starting state should be a superposition over elements in our domain of the hash function. The underlying classical group action is very easy. It's G is the same as X, is integers, and the star operation is just a plus operation. And the starting algorithm just creates the state phi. And to act on a state with the group element, we just apply this unitary, which takes R, and this adds this phase that depends on, that is G dot HR. And so the final state would be just uniform superposition, and then we have this phase. That's the act operation. This is easy to see that this PG and PH, it will give you PG plus H, where plus is the group operation. Okay, so I'll just briefly talk about how we prove security for the hash-based construction for the DDH setting. So in the first case, we have these three states where G1 plus, we have G1, psi G1, psi G2, and psi G1 plus G2. Oh, okay. Yeah. So yeah, when we just open these states up, so we just apply act, we get the following state. And then the main idea is that in the first case, we'll get this state. And when G1, G2, G3 are random, we get this other state. And then we can prove that as long as this function in the phase, if it satisfies this function, some injectivity properties, that's enough to prove that these two distributions are indistinguishable. And so now for quantum money, this is the quantum money scheme from Zenry, from classical group actions. And when we just replace the classical group action with the quantum group action and just open up the state according to the act operation, then we basically, when we're summing over all group elements, the root of unity zeroes out, and we just recover the exact same state that we know from the non-collapsing hash function construction. Yeah, so this is just basic math, and you just open up the hash-based construction. There's nothing, yeah, much going on here. Yeah, and that's it. Yeah, thank you.
We have time for one or two quick questions. If you want to ask a question, you can go to the microphone. Okay, maybe let me ask a quick question. So do you see this construction being plausibly like the computationally secure one? Do you think that there is a way to make them secure even if I have an NP oracle?
Even if you have an NP oracle?
Yeah, that you can query with respect to this hash function H.
Oh, I haven't thought about it. Yeah.
Okay.
Possibly.
Okay, so that was the last talk of this session. So let's thank all the speakers again.